Greetings of the day. I am Dr. Vaibhav Jain, Student Branch Advisor, ASHRAE, Student Chapter MAIT. First of all, I would like to thank ASHRAE Society for providing us the grant of $4,470 to work on the project Design and Development of Household Refrigeration System assisted with Two Phase Ejector under the Project Equipment Grant Scheme 2020. I, with my students, are here to present you with a basic understanding of our proposed project and what we have done till now and will do in near future, and how we are on the track towards its completion. The ASHRAE student members are involved in the development of this experimental test rig, and work is divided under my supervision so that every student is able to understand and learn the process of fabrication closely. Now, my students will demonstrate you how the work is going on.
Our team includes a total of 10 members which are part of the ASHRAE MAIT chapter. Now, one by one, my teammates will give you a brief overview of what we have done up till now and what we will be doing in the near future and move towards the project's fabrication.
Refrigeration system operates on a series of consecutive thermodynamic processes that form a cycle that returns the working substance to the same state. A thermodynamic refrigeration cycle removes heat from a low temperature subject and rejects it at a high temperature. In this project, we have aimed at working on the dual evaporator ejector expansion refrigeration cycle, in which a two-phase ejector is used as the expansion device to recover the expansion work. The results show that COP of the system can be improved by about 10%. In thermodynamic modeling, we have explained two mixing models used for our research and investigation, that is CPM and CEM. As we will move forward towards the fabrication of the same, we will get to learn the applicability and efficiency of the system in today's industrial arena.
A household refrigerator works on the principle of vapor compression refrigeration cycle. Here, we try to develop a more efficient system. For that, we use a two-phase ejector. Ejector does the pressure recovery for the condenser. Therefore, low compression ratio is required and it reduces the size of the compressor and hence energy consumption. This system proposes a good alternative to the basic VCRA system, and we have worked on exploring its advantages and application. The EVCRA system consists of a compressor, an ejector, a condenser, and two evaporators with different evaporating temperatures. The detailed working of the same can be seen from one report, and we have begun the fabrication of the same, and in next few months we will validate the result from the fabricated system in a refrigeration lab in our college campus.
We have gone through many research papers and theses and have obtained a basic idea of the system and its working. We have learned the importance of the system in today's scientific arena and its need in the industry. In two-phase mode, we recover energy which we lost in previous cycles of operation. Ejector increases the efficiency of cycle by consuming less energy. Our motive behind choosing this project was to learn and explore the new and better ways. An already deployed system can be improved upon, and we as engineers tend to find ways in which the work takes minimal effort and produces the maximum output. This study is also important, especially in today's world where sustainable models and techniques are given the utmost importance. The system has also not been that much in use, so that also contributed towards our motivation for the same.
The inner workings of the system have been explored theoretically and will be applied practically in the next few months. We have learned about two different models of an ejector and have carried out theoretical analysis of the same up till now. They are constant pressure mixing model and constant area mixing model. In constant pressure mixing model, motive nozzle exit lies before the inlet of constant area section. The supersonic stream from the motive nozzle is at a very high velocity and very low pressure. The primary fluid thus sucks the secondary fluid through suction nozzle, and mixing of two streams begin. During mixing, collisions of fluid particles of two streams result in rise of pressure. In constant area mixing model, motive nozzle exit lies at the inlet of constant area section as represented. The primary fluid from the motive nozzle and secondary fluid from the suction nozzle mixes together in constant area section completely. During mixing of two fluid streams, collisions of particles of two streams increases the resulting pressure from motive nozzle exit and secondary nozzle exit to mixing area. The mixing of fluid stream continues up to the inlet of diffuser section. In this way, pressure increases slightly during mixing in constant area model.
Coming to the computational procedure, we used the thermodynamic model described to you by my fellow teammates and presented a schematic diagram as seen from our report. This led us to further analysis by developing programs on EES, Engineering Equation Solver, to compute various performance parameters for both constant area mixing method and constant pressure mixing method. For these programs, we first developed an algorithm for CAM and CPM separately. After computing all the performance parameters, we made several observations which we have discussed as part of our results in our report.
We saw during our theoretical work and after compilation through EES that the CAM model is more efficient than the CPM model. But since the analysis and compilation is much more time consuming and requires much more work than CPM, we have presented the theoretical analysis through CPM only. We have found theoretical results through one method, but when we will complete our fabrication, we will validate the result through both the models. Since we require an extensive analysis before deploying the system for the use, we need to explore each and every aspect of the system carefully, and we will definitely do the same through our fabricated model.
In this project, we have learned a lot thanks to ASHRAE and Dr. Jain who brought us this opportunity. For example, till now we had just learned the Gauss-Tudela theorem, but now we have applied it as a part of our exergy analysis of the various components of the proposed system. Thermodynamics has been one of my favorite, and with the project, our knowledge came into the practical aspect. We are on the path of the fabrication of the whole system, in which we will assemble all the parts and assess the feasibility of the system by validating the results and explore whether practically it is justified or not, and whether it is suitable for the
Household refrigeration system or not.
Now we have done the market analysis too for our project's fabrication. We have begun buying the necessary components required for the same and will continue the process and complete the fabrication soon in the next few months. We will finish our project in the timeline promised and also within our budget of the fund provided to us by ASHRAE. We will explore practically whether the COP actually improves as compared to the VCRS model and how the system proves to be effective in the real world. We will check the validity of our results obtained theoretically and see whether they come true through our fabricated system, especially the 10% improvement in the COP.
Ejector are the static devices with no moving parts, which makes them reliable and requiring no or minimal maintenance. They can handle phase-changing streams and two-phase mixtures. They are widely used as mixing devices and for pumping corrosive fluids, slurries, etc. In other industries, they are used in gas-liquid reactions and for the purpose of absorption too. The main factors which affect the performance of an ejector are the system conditions and ejector structure. We can use CFD to visualize and enhance geometrical parameters for ejector systems. As explained, we are on the track to fabricate the project and employ the above techniques for the fabrication and analysis and submit a full-fledged report explaining the system and its results obtained and its extent of applicability in the HVAC and our industrial area.
We thank ASHRAE for giving us the necessary funds for the project, and we will definitely deliver on your expectations with the hard work and dedication which we have shown towards this project since its inception. Every year, around 240 students study the course of refrigeration and air conditioning at MAIT, and this project will definitely benefit them to have a practical understanding of what they have learned. This will be a good opportunity for the students and the college too, as a new system will become a part of the RAC lab showcased in the video. Lastly, we thank Dr. Jain, our student branch advisor, without whose guidance we would not have been able to even think about this project. His constant efforts and dedications have what brought us all the laurels to our chapter in just 2 years. We thank ASHRAE, Dr. Jain, and all the professors at MAIT. Thank you.